Yeah, thanks very much. So today I'm going to share a little small insights from my group that we have developed in the last couple of years with you. So it's a quantum excitation of hidden order and the thermal transport of hidden particles. And before I started, I want to advertise this conference next year. So this is the 10th International Conference of High Frustrated Magnetism. And this international conference is held every two years. So the 10th one will be in Shanghai 2020 from May 17th to the 22nd. So the half of the organization committee actually are in this conference. So please pay attention to this conference. Yeah. So this is our outline. So first part of the talk will be explaining, try to motivate or try to understand this hidden order or intertwined multipolar orders and then associated quantum excitations in this triangle that is magnets. So this is experiment, this is theory, agree perfectly well. The second part is about thermal transport, thermal Hawk conductance in basically spin-ons or monopoles in quantum spin liquids. And this is mostly with my student, Yonghao, who is also here. So hidden order is a popular culture, popular word in Western culture. So this hidden order in brain, and actually a couple of days ago, undergraduate student, sent me her, course history, let me to review. So I realized there is a hidden order in daily life. So Hong Kong is pretty Western, so there is a course named after hidden order. If you Google, you can find a lot of books. Hidden order in art, hidden order in corruption. There are many other hidden orders. So what's hidden order in condensed matter? So this word, this concept was introduced in condensed matter about 30 years ago due to this discovery of this material, uranium ruthenium silicon. So this material, if you apply pressure and cool the temperature, so this material has both alternate electron and a local moment. So uranium provides the local moment. So it's 5F electrons. So if you cool the temperature around 17 Kelvin, apparently there is a phase transition. So this experience in heat capacity, there is a peak. And if you do entropy measurement, entropy estimation, there is a huge entropy drop at this 17 Kelvin transition. And below this temperature, the system enters some kind of order which is unclear from any kind of experimental probe. And at very, very low temperature, there is a simple activity going on here. So this is called a hidden order. And the nature of hidden order was not understood. Yeah, so this is second order transition at 70 Kelvin, there is a huge entropy drop. And this order parameter associated with this hidden order is not unknown after 3 decades. This material has a lot of degrees of freedom, local moments, conducting electron. So this is lots of measurement can be carried out because of this material has many kinds of degrees of freedom. So you can implement many kind of experiment, optically, scattering, neutron scattering, X-ray, or transport or oscillation, all kinds of measurement. So there are also, in addition, a lot of theoretical proposals. This is a list of them summarized in this great paper in 2013. So that was 5 years ago. There are still new proposals. So these are many different orders being proposed. These are different multipolar orders and different. So the nature of this hidden order in this material has not been resolved yet. So how do we, generically, since this material, many other systems has been. This word, hidden order, has been used in other systems. So how do we identify the nature of this hidden order? So there is a simple proposal. We have this called it's rather simple. It's called orthogonal operator approach. So imagine this hidden order means you cannot this order parameter associated with this order does not directly couple to your experimental probe. So that's why it's invisible. It's almost the dark matter of the condensed matter. You cannot really resolve it, cannot really detect it with your current experimental probe. But the idea is that if you can find a physical observable that can be easily observed experimentally, and this physical observable, whose operator, is orthogonal or do not commute with the proposed hidden order operator. If you find an orthogonal operator, orthogonal to this hidden order operator, and these observables, as I said, is easy to observe experimentally. So the dynamic correlation function of this orthogonal operator will necessarily reveal the structure and underlying nature of the hidden order. So you can just find these field observable that are orthogonal to these hidden orders. So this idea has been summarized in these two works by us. Yeah, so let me use this idea to apply to this experiment, this material. So this material is not our motivation, it's an application of the idea. So this work has been mostly collaborating with my postdoc. He's a theoretical hero underlying this collaboration. And these are two experimental colleagues from Fudan University doing neutron scattering measurements. So this work has been accepted in Nature Communication, will appear there. So this is actually a motor insert. This material is insulating material, and this guy, which is not often a magnetic ion, it's not being often studied. It's called tellurium, 3+. It got 12 electrons, 12 F electrons. So you form a local moment and form a triangle that is. So it's a triangle that is magnet. So if you do this, conventional measurement, susceptibility measurement, by applying field along normal to the triangular plane, you see a large response. But if you apply field in the AB plane, in the triangular plane, so there is no response. So likewise, if you do magnetization measurement, so if you apply field normal to the c direction, or parallel to the c direction, or normal to the plane, you see a large magnetic moment. If you apply field in plane, that's nothing. Right? That's nothing. So heat and capacity measurement, see there is around 1 Kelvin there is a peak. There seems to be a transition there. So just from these susceptibility magnetization measurement, one can immediately conclude that this AB plane moment is not visible. It's hidden, right? Or it's just not there. Maybe it's an Ising moment. It looks like maybe it's Ising, So originally these people, his group, Gaden was a group. He concluded that this is maybe Ising spin. So then it's completely trivial if it is Ising or triangle. That is, we know the result in 1949. So yeah, so the transverse component or in-plane component is completely hidden. So only the c direction is visible in magnetic fields. So that's the thermodynamic measurement. So this is the neutron scattering measurement. So in the elastic measurement, there is a Bragg peak at the K point, at the momentum K in the branch zone, and this is the intensity. Around 1 Kelvin, its intensity becomes large. So the transition temperature is around 1 Kelvin, which is consistent with the heat capacity measurement. And this is the, in the momentum space, there is a peak at K point. And if you measure the intensity, you measure this peak along c direction, momentum along c direction is flat. So it's concluded it's a two-dimensional material. So it's a truly two-dimensional triangle lattice material. So the system orders antiferromagnetically at momentum K. So K is basically the momentum corresponding to what we usually study triangle lattice magnet, which is this 120-degree order wave vector. Well, it doesn't mean this is 120-degree order, just the wave vector is identical to the state of this 120-degree state.
So you mean it's a 3 sublattice order?
Yeah, it's a 3 sublattice order. This one can conclude. Yeah. So this is still the Bragg peak, and this is the experiment. The upper panel is experiment. The lower panel is theory. So the upper panel is the experiment. So you fix. This is the momentum, one direction and the other direction of the two-dimensional momentum, and you change the energy from 0.1, 0.2, 0.3, 0.5, 0.9. So basically, if there is some energy band, you change the energy gradually. You see the cut, right? So this means there is a well-defined spin wave-like dispersion, right? Which cannot be, that means the system cannot be Ising degrees of freedom. If it is Ising degrees of freedom, which orders anywhere magnetically, so the dispersion will be completely flat. Ising spin does not have quantum mechanics, so there's no dispersion at all, right? Yeah. It cannot be. So the other conclusion it's not very clear is that the other conclusion is not obvious is that there must be some transverse component being ordered. So if the transverse component do not order, so this thing would be a two-magnum continuum. That requires some experience, but there will be two. You have a question?
Yeah, what does it look like in the usual K versus E versus K?
Yeah, this is this. Yeah, so this is energy one momenta. So really should be a three-dimensional plot, right?
This is now experiment, right?
So the up panel is experiment. Lower panel is theory, which I will explain. Yeah. So the one conclusion one can make is this certainly cannot be Ising. If it is Ising, it's going to be completely flat. So the other conclusion is that there must be some transverse component, AB plane component being ordered, which is hidden in any magnetic measurement. In our magnetization measurement, we don't see any AB component of the spin of the moment. So, but in this dynamic measurement, that immediately indicates there is a hidden component which is AB plane order, must be ordered. If it is not, this will be a two-magnum continuum.
Say it again, sorry. Why it's not ordered in the plane, according to you? Why it's not just 120 degree in the plane?
Yeah, so the K point order is a measurement of the C component of spin. So this neutron diffraction measurement. So this measurement it really measures the C direction. So the neutron spin coupled to the magnetic moment in the same way as we apply field to the magnetic moment. So only C component of spin is visible by neutrons. So that means you can only measure the structure of the spin in the C direction, right? So AB plane, if it is order, is not visible. If it doesn't order, it's not visible either, right? So that AB plane moment, the magnetic moment in the AB plane is invisible, right? So we apply field in the AB plane, there's nothing there. So AB plane order is invisible, right? So that's the message I want to deliver.
No, this is a uniform field.
There's a uniform field.
So you cannot exclude that you have.
Well, if you apply field, you always get polarization, regardless whether it's antiferromagnetic order or ferromagnetic order, right? So you don't see any response. Right? So that means the AB plane, moment as if it disappeared. Right? It really is not disappeared. It's there, just that we do not see it. I'm delivering the message of hidden order, right? It's hidden, right? So this is hidden. So it's not, but from this experiment, if you think a little bit further, it's not really hidden, right? If it is truly Ising moment, if there is no AB plane moment, so this dispersion will be completely flat, right? It will be flat. Just doing some calculation in your mind, it's going to be flat, right? So if this AB plane order does not exist, if there is no AB plane order, that's Sx, Sy, the expectation value of them is 0. If it is that, if it is state of this kind, then this dispersion will be a two-magnum continuum. It will be not a well-defined spin wave dispersion. It will be two-magnum continuum. It will not be some coherent spin excitation. Right? Because if you write Sz equal to S minus A dagger A, if you compute the correlation function, that will be two-magnum continuum. So the presence of a well-defined spin wave dispersion be measured here is a strong indication there is a AB plane component which is invisible experimentally, but must develop some kind of order. So that's the conclusion. Must be non-zero. Otherwise, you cannot have a coherent spin excitation in this spectrum. So that's the dispersion in this experiment, this theory, along this cut of momentum lines. So this energy momentum. Yeah. So how do we understand that, right? So this looks like it's some kind of non-Kramers doublet, if we're familiar with that. So the AB plane is the quadrupole moment, the C direction is dipole, and you don't see the quadrupole. It's wrong. This is actually they're not non-Kramers doublet. Not non-Kramers doublet doesn't not mean it's a Kramers doublet. It's just not a non-Kramers doublet. Yeah. So the name is not very great, but this is a yeah. So it's an even number of electrons per side. It's most likely to form a non-Kramers doublet because it's an even number of electrons. So it's a non-Kramers ion. So this 12 is 3 plus even number of electron 12, and if you do these Hans rules, so the total moment J equals 6. 6 is particularly special. It's an integer multiple of 3. Yeah. Turns out that the ground state wave function is a singlet. It's always a singlet, and there is second excited state first excited state is also a singlet. So the wave function you can write them down, which is a combination of 6 minus 6, Jz plus minus 6. There's some like Jz equal to 0, Jz equal to plus minus 3. These are very small contributions. The system is almost Ising because the moment here. So the magnetic moment is almost, if you apply C field direction and large enough, you get almost polarized. This is almost equal to J, Z equal to 6. So it's almost Ising, but it's not Ising. There is always a splitting between them. So if it is only this state being contributing to the magnetism, you don't see any magnetism. Singlet doesn't play any role in the magnetism. So it's these two states. The first ground state and first excited state. These are well separated from other excited states. Only these two guys are contributing to the low temperature magnetic property. Then you can build up effective spin 1/2 operating on these two singlets. So the reason it is singlets because this is 6. So if you apply 3/4 rotation to that, it stays invariant. So this 2 pi over 3 rotation, right? So times multiple 6 is equal to 4 pi. Right? E to 4 pi is 1. So these two states that stay invariant. It's a magic. So these are two singlets under any kind of 2/4, 3/4 rotation of the D3D Poynting group. So they are truly singlets.
How big is the energy scale?
Yeah, it come next.
For other height.
Oh, this is very high. This is a couple hundred Kelvin. You can forget about it. Yeah, these two states are very close in energy because the form of the wave function are very similar. So that's why they're close in energy, right?
So close.
Yeah, lowest two states.
Yeah, but when you say close, which is the order of magnitude? Close.
You mean this energy, or
yes.
this is
0.6 million.
Yeah, this energy scale. Yeah, so you can model this. Basically the wave function are pretty close, and the separation between them are actually pretty large. The distance between 6 and minus 6 is 12. Or then it might be 0, but the 6 between 0 is 6. So you will require flipping like 6 or 3 times, which is a high order process. So then you don't have any transverse spin interaction. Then only Ising, dipolar interaction between them, first neighbor, second neighbor. And then there is a transverse field here. So this is because there is an intrinsic splitting between these two states. Then you introduce the on-side transverse field to describe the splitting between these two states. So then it's become an intrinsic quantizing model. So it's an intrinsic one because the transverse fields are has an intrinsic origin. It's not like I apply a transverse field externally. So this is very different from extrinsic quantizing model that has been pursued by, for instance, Songbin a long time ago on this carbon iobinate. So this is a paragraph in a paper I wrote but unpublished. So these are carbon iobinate and barium copper vanadate. So strontium copper vanadate. These are just copper 2+. So these are so it's an emergentizing spin, but then if you apply transverse field, it generates an extrinsic quantizing model. So the transverse field are generated by hand, right? So in contrast, this quantizing model, the transverse field are generated intrinsically. So this.
You determine the J2 and J1, J2 these parameters.
Oh, you can fit experimentally.
So J2 is almost negligible.
Yeah, J2 is very small. J2 is very small.
It's an F electron, right? So
It has to be very small.
Has to be very small.
Yeah.
So H is crystal field splitting.
Yeah.
Or like J1, J2, you get from spin-wave dispersion, or what? How did it?
Yeah, you can determine from rise temperature plus these fitting of the spectrum. Yeah.
So if you add an external in-plane field in this effective model, what does it look like?
No, if you apply field only along z direction, you cannot apply because from the magnetization measurement, x y component do not respond to the external field. These are high order multiple moment, 2 to the 6th or 2 to the 3rd multiple orders. Yeah. So.
Sorry, but if we were to apply, so if we look at your equation and the way you have written that, I could substitute your last term is like, you could also put it as an external. So this you say it's from the crystal field, but you could also have an external field coupled to SIY, and then you would get the same response. So why do you say it's not coupling?
No, so if we apply field externally, the field only coupled to z component. So x.
So you say that you need this intrinsic term to have the y component coming in.
Yeah, this thing is time also even, and this thing is time also odd.
Okay.
So because the time also even, it does not couple to the external field. Yeah. No, I define sy this way, sz this way, because the wave function is not that diagonal in the sz basis. It's a hybridization of 6 and minus 6. Right. So then, this 3 sublattice order being measured experimentally. It's a 3 sublattice SZ order, should be more precisely, SZ order. It's actually a quantum effect. It's arising from the geometrical frustration and quantum order disorder. This is even known long time ago by Sonny Moster's numerical work. So these, if you just consider transverse field Ising model, in a weak field regime, this thing, can be mapped into a quantum diamond model and do a honeycomb lattice. There's a 3 sublattice order. It's ordered by disorder effect. And if then you map back this quantum diamond model order into this spin configuration, it's this thing. It's not written, well, the original paper is not parameterized this way. It's like, it's up, down, up, down, up, down, up, down. This spin is pointing the transverse direction in a weak field regime. Right? So if you increase the field, the 3 sublattice structure survives, but there will be a strong tilting to the in-plane direction. So this is basically the configuration drawn here. So this is the spin configuration of this ground state.
That's actually a pseudo-spin configuration?
A pseudo-spin configuration, yeah.
The z component.
Only the z component is immeasurable,
Right.
and the in-plane component is hidden, right?
So, can I just check I'm understanding? What I think you've done is to take a non-Kramer's singlet ground state, describe this by a pseudo-spin for a non-Kramer's doublet, and then introduce this field to achieve the splitting.
Yes.
Which you're saying is acting like a transverse field. And it's going to give you a dynamics and things.
Exactly.
Is that right?
Exactly. Yeah. It's a quantum model, and.
So this 3 sublattice SZ order is preferred by that J1, J2 that you are considering.
No, only with J1, J2, it's there's no order. It's basically primarily J1. That's always degenerate, right? So you need a transverse field to generate the quantum effect that select this particular 3 sublet order. Without the transverse field, you don't have any order.
Right, so in the presence of this transverse field and J1, J2, this is the favored.
Yeah.
Well, if you have no transverse field, but if you have J1, J2, you have another type of order.
Yeah, if J2, here J2 can be ignored, then just J1 is highly degenerate state. J2 just introduced for making the splitting a little bit better of intensity. It's not really, you can kill J2.
No, I was just referring to your statement. If there is no transverse field and infinitesimal J2 orders.
Yeah, you can get some kind of strange order of some type.
It's well documented.
Yeah, sure. Yeah, so now I'm expanding. Question, yeah.
Yeah, so I know that the Z actually is like a high spin component, so flipping it with the magnetic field in plane is hard. But with the splitting, what is the lowest order of the in plane field would contribute to this system?
What does it mean? I don't understand.
Oh, I'm just saying I do perturbation theory. Like at what order does the in plane field comes in?
Oh, this is. It depends on it. Maybe like third order, maybe even higher than that. Yeah. So the denominator will be the energy scale of the energy separation between the lowest two doublets, two singlets, and the highly excited states. The energy gap will be that. The denominator will be that.
So the transverse field does not help that much.
If you apply magnetic field, at dominant energy dominant effect will be coupled to this component SZ.
Sure.
Will be coupled to SZ. Yeah. Yeah. Some my student, my postdoc, they are actually doing a numerics, including effect of external field along SZ direction. They have some first diagram. So the transpose components are hidden. I was advocating about hidden orders, and it should be non-zero according to. Otherwise, you don't see any dynamics, right? So now come to this dynamic measurement or this orthogonal operator approach. So SZ is orthogonal to the transpose spin component Sx and Sy. So the dynamics of that can be easily detected by neutron scattering, and actually all the SZ can be measured by neutron scattering. So you're doing regular neutron scattering as if you are doing polarized neutrons. You are doing SZ correlation function, and if you do the calculation, you will get basically this result, and this result. Yeah. So this is the application of this orthogonal operator approach to understand the intertwined multipolar structure and quantum excitation in this material. So this is a simple application of that. Yeah. So this orthogonal operator is SZ. Transpose components are hidden. So let me summarize the first part. So the interplay between geometrical frustration and the multipolar local moment. This is a separate summary from hidden orders. Can lead to some rich physics and excitation. So the manifestation of this hidden multipolar order is rather non-trivial. You need to combine both static and dynamic measurement together to conclude a unified story. So the orthogonal operator approach is quite general actually. It can be used to reveal the dynamics of hidden order, and this can be adapted into many other hidden orders. For instance, if one is interested, you can apply this idea to this 30 years old puzzle of uranium ruthenium silicon, just to find out this orthogonal operator. Actually, over there, because there are so many degrees of freedom, there are actually a lot of orthogonal operators. You just check all these different orthogonal operators whether they can give you a unified description of the system. So finally, which is not mentioned, that there can be a non-trivial Berry phase effect between this hidden component and the visible component. And they can give you some extra physics on the dynamic property of the system. It seems this thought has been hinted in some work by Hipperson and Ian Fisher, they had this work on. It's actually the same ion, tellurium silver and tellurium gold compound.
Like SY of your pseudospin, maybe they can also couple to magnetic field even power or something. It's the time was even.
Yeah, it's if you apply a very large field, very large field with a small coefficient.
You know how? What will be the lowest power?
No, I didn't work on that. Maybe 6 power.
6?
Maybe 6.
Why 6?
Yeah, maybe 6. It's not a quadrupole moment. It's like a 2 to 6 something. I don't know the name. 2 to 6 order multiple moment.
It's like angular momentum 6.
Yeah.
Angular momentum 6.
Yeah. It's angular momentum 6. Yeah, it's the 2 to 6 order multiple degrees of freedom, something like that. There would be some good English for describing this.
Some Latin.
Hexagonal, I don't know. Yeah. Yeah. So I'm doing well with the time. If there's no question, let me just continue to the second part.
Just one maybe.
Yeah.
Description, but when you say non-trivial barrier, just for example, when you have, suppose take nail and BB space, which don't commute. So then if you do imaging in the defects of nail, you find BBS and vice versa. Is that what you meant, sort of, broadly speaking?
Yeah, I'm a bit vague on this. I'm just very vague. If you do, yeah.
But at least that's an example.
That's an example. Yeah, that can be an example.
Effect, and that's about non-commutative.
Yeah. So in this work, it's about this alloy, TMAU2 and TMAG2. So TM provides this some kind of moment I was talking about, but hybridized with conducting electron. So then there can be some effect, which is not it's hinted at there. But it's not obvious whether it lead to anything significant in that context. Yeah, we can discuss about this later. Yeah, if there's no question, let me continue to the second part. I've been spending 1 year to develop this topic. So I try to understand. Our group try to understand this thermal Hall effects in quantum spin liquids, mostly by my grad student Yonghao Gao, and Xiaotian is also here. Where is Xiaotian? Yeah, Xiaotian is here. So he did extensively on this particle U1 spin liquid. It's a monopole thermal Hall effect. So yeah, so this is maybe it's a motivation. So this is a very famous measurement of thermal Hall half quantized or quantized thermal Hall effects in lithium trichloride. When you apply, everyone knows this experiment, right? If you apply field, there is seems to be about 7 Tesla. Actually, the measurement is from 4 to 5. 45 Tesla regime. There is kappa x bar over t. There is a plateau that looks half quantized. Yeah. So one can raise a lot of questions about this measurement. Also raise a lot of questions about generically on these honeycomb KITP materials, both at h equal to 0 and h non-defined field and 0 field. You can raise a lot of questions. I'm not going to raise many questions here. It's actually easier to be destructive than to be constructive. So I'm not going to be destructive. So let me just. This is a very interesting measurement. I'll try to. Part of the thought is original from there. So I'm also very motivated from this experiment by Hiroshi Zenji and Yamashita from Japan. So this is on this is a Wolfside material. It's actually the first Kagami spin 1/2 material. It's before Herbig-Smith. Although it's not a perfect Kagami, it's distorted Kagami, but it's the first spin 1/2 Kagami, single crystals. And this is magnetization measurement. There is some plateau going on.
Which one? Wolfside?
This is Wolfside.
Yes. Okay.
This is Wolfside. And this is the thermal Hall conductance measurement on Wolfside and caprolacite. They show this very large thermal Hall effect, and non-monotonic. Apparently have different sign. At very low temperature, because warp side at like a sub 1 Kelvin develop some order, some weak order. There's some ordering going on. You don't worry about this data over here. But the sign of these two materials are different, and they are not. So the question is why there is a finite and non-zero thermal Hall effect in this motor insulator, a strong motor insulator. Why is non-monotonic? Why these materials have different sign? They're all Kagami materials. Why have different sign of this? Yeah. So that's the question. Large thermal Hall effect in spin 1 half Kagami magnets. So this is my trivial understanding of the thermal Hall effect. So thermal transport in motor insulator, in terms of energy scale, this is temperature. So when the temperature is huge, there's a trivial regime. It's a trivial paramagnet. It's doing high temperature series expansion. This is not very interesting. So this intermediate energy regime is where no one understood. No one understands is the transport of ion particle. There is no good understanding. It's not a ground state. It's not the infinite temperature paramagnet. It's some other intermediate where correlation just developed. It's the intermediate temperature energy scale. It's not well understood either. Not well understood. So what we can understand is this low temperature regime, where the system is proximate to the ground state, and there can be a quasi-particle description or various quasi-particle description depends on the ground state. So the quasi-particle description one is this when the system orders. When the system orders, so little bit of temperature, you create magnons, and these magnons can contribute to your thermal Hall effect. So this is some work, Y magnon with Young-Beck and Dion balance, where this Y magnon at finite temperature can contribute to the thermal Hall effect. So this is like a non-trivial barrier phase, non-trivial barrier curvature of these magnon bands due to this presence of Y points. Yeah, this is so magnon thermal Hall effect is being well understood because there is a well-defined quasi-particle. We know the description very well, and this is a particle ferromagnet. The vanadium is a magnetic ion. It forms ferromagnet. Actually, not perfect parent because DM interaction is a distorted ferromagnet. And the theory description agree with the experiment very well. Yeah, so the dots are experiment, the curve are theory. And this is a Kagami ferromagnet. Also because of DM, there is a natural, magnon band, magnon barrier curvature distribution of the band. You can see this non-trivial magnon thermal Hall effect. So these are simple and well understood. So the low temperature regime 2, where the ground state is disordered state, where that's a very beautiful idea by Philip Anderson, proposal of quantum spin grid. Yeah. So I don't need to mention the history. So I just amazed that in the 1970s and 80s, so lattice gauge theory were developing. So these Anderson proposed this idea in the 70s and 80s. It seems we need to use lattice gauge theory with these 5 quantum spin liquids, and just amazed the different branch of theoretical physics can eventually emerge. And in the 70s and 80s, we don't see any connection between these two different theories. Now seem to they should converge. Yeah, so we need to use a so-called lattice gauge theory to describe quantum spin liquid. So there's some emergent gauge structure by fluctuating mean field theory. I would like to use Xiaogang's description. You cut the spin into halves, or into spin-ons, into whatever. So glue them back by gauge theory. This is the formal procedure of trying to establish lattice gauge theory by cutting spin to fermion spin-ons, and then glue back by gauge theory by including the fluctuation of the mean field, which generate gauge fields. So I'm interested in the physical property of quantum spin liquid. What are the non-trivial physical property can this lattice gauge theory understanding brings, right? Bring to us. So one immediate consequence if the lattice gauge theory is in a deconfined phase, so then we have spin quantum number fractionalization, And immediate experiment consequence is this consequence of fractionalization. We would see a so-called continuum of excitations. So neutron comes, imagine do a neutron scattering measurement, inelastic ones. You flip a neutron spin, create an integer spin excitation. Because of fractionalization of spins, so this should be shared by two spinons. So the neutron loses its energy and momentum, and this energy and momentum have to be shared by two spinons. If we list the energy momentum conservations, there are more variables than equations. So that means there is a continuous solution of these energy momentum conservation laws. And this is an example of one spin liquid candidate material where I see a broad continuum of spectrum. So basically the shape of this, the structure of this continuum put a strong constraint on the possible candidate spin liquid ground state. So you can build a connection between the spectrum and the kind of spin liquid. Consequence 2, another immediate consequence, because of fractionalization, fractionalization is an independent phenomenon, independent from other physical properties. If you impose symmetry on top of these fractionalizations, so you will get a symmetric fractionalization. So symmetry corresponds to some kind of quantum number, you get a quantum number fractionalization. So this is an example of transcendental symmetry fractionalization, where the spinon hopping on lattice will experience some pi flux. So then the transcendental symmetry of the spinon is being realized projectively. So it's a projective symmetry group of transcendental symmetry. So then the spectrum of the two spinon continuum will have some enhanced spectral weight, spectral intensity. So the periodicity will be, for instance, half of the Brillouin zone rather than the whole Brillouin zone. So it has enhanced spectral periodicity, which is a very important phenomenon. So these are all consequences of this spinon gauge coupling, when the gauge theory is in a deconfined phase. So these are consequences on the spinon matter themselves, right? So this is a consequence due to the matter gauge coupling, and the lattice gauge theory is in a deconfined phase, and we look at the matter sector, right? So the important ingredient in the theory is that the matter has a gauge charge. So there is a matter gauge coupling, right? So deconfined and fractionalization are consequences of matter gauge coupling in the deconfined phase. What would be the somewhat more direct evidence of the matter gauge coupling itself? Right? So we want to understand this particular coupling. Right? Now in physics, everything will be examined experimentally. Right? So this is what's the evidence of matter gauge coupling when the matter hop on the lattice and experience a background gauge field. And this means the matter carry a gauge charge. What would be the evidence of that? To motivate this question, let me just go to the context of electrons. Right? Electron carry electron charge, or electron carry a U1 gauge charge. There is a Coulomb-Lyapunov interaction between the electrons. By saying that, that means this is a consequence of electron phonon coupling. Electron carry a U1 gauge charge coupled to a U1 gauge field, and this phonon mediate a Coulomb interaction between the two electrons. So in condensed matter point of view, the signature of this matter gauge coupling, or when the electron hoppers and experience U1 gauge phase, is this quantum oscillation measurement in condensed matter physics. So if we apply field, the electron hopping on that will experience a flux and form Landau levels, and then you can get this quantum oscillation due to the population of different Landau levels. You get these quantum oscillations. This is a strong indication that this is a signature of electron coupled to this background magnetic field. So people use this idea to understand the quantum spin liquid by Alexei Mokhonich, where he first point out there can be a large orbital magnetic field on the emergent fractionized spinons. For a spinon-forming surface state for this organic material. So this organic material is a weak motor insulator, the charge gap is not very large. So basically, it's proximal to a metal. In other words, the spin-on emerged in this context is not far from an electron. It's almost an electron. So it's an electron in a short distance. In a long distance, it's a spin-on. So the microscopically, because of strong charge fluctuation, they generate ring exchange, force spin ring exchange. If you apply field, the field will insert in this ring exchange. They will generate flux, and the flux will enter this ring exchange. And then will indirectly impact on spin-ons. So the spin-on will experience the orbital magnetic field through the ring exchange. You get all these quantum oscillations. So that's a very, very, very cool phenomenon. But in this context, the spin-on are not far from electrons. So it's somewhat not too surprising, because the spin-on are not far from an electron. So this is the idea. You use the external magnetic field to control the emergent internal magnetic field. So the significance of this work is that. So then, because of that, you can generate a thermal Hall effect. Because you apply an external magnetic field, you can generate internal U1 gauge flux and twist the motion of the spin-ons, then generate a thermal Hall effect. But this is not really surprising, because the spin-on in this context is not far from an electron. It's almost an electron. So the physics over in this context is very proximal to a fermi liquid metal. But this material we point out, we studied this Kagami material overside, capacitor. These are strong motor insulators. So the charge fluctuation, charge gap is huge. The dominant scale in the problem. So you don't worry about the charge fluctuations. So the degrees of freedom in this context are spin. They are not electron. The spin-on emerged from this context has no resemblance of to a physical electron. So the excitation are spin-on, do not carry an external U1 gauge charge at all. And the coupling to the external magnetic field is only Zeeman coupling. It's unlike this weak magnetic field or weak motor insulator, where the coupling to the magnetic field can have this orbital coupling. So this is very different. So there's only Zeeman coupling. There's no orbital coupling. How can this magnetic field, with only Zeeman coupling, come and twist the motion of the fractionized spin-ons, neutral spin-ons, and create the thermal Hall effect? So our purpose is to understand the physical property of quantum spin liquids. It's not try uniquely conforming quantum spin liquids. So there are 4 different cases of thermal Hall effects, in this strong motor insulator. So we summarize. So we list here. So some people may be familiar with some of them. So in color spin liquid, where there is edge state, you will always get a quantized Hall effect even without the magnetic field. So for gapless due to quantum spin liquids, such as this KITP spin liquid without magnetic field, if we apply magnetic field, you can change the band structure topology of the spin-ons and create a chiral edge. That's the example. Color spin liquid is the example. So this is very much like one, but applied to quantum spin liquid with gapped gauge sector. So if it fully gapped due to quantum spin liquid, the effect of field just rigidly shift the spin-on bands. There's nothing significant going on in this context. So what we are interested in is this the first one, where the gauge sector is continuous. The gauge sector is continuous. So then external magnetic field comes in and modify the internal continuous gauge field, and then by indirectly twist the motion of the magnetic field and generate a thermal Hall effect. So this first part we are going to first point we are going to illustrate, and the one which understood by Motronish and Patrick is the one in this first point, where the external magnetic field comes in and generate an internal gauge flux for the fractionized particle and twist the motion of these spin-ons. So, but in this context, as I mentioned, because of this, it's a weak motor insulator. The charge gap is very tiny. So the coupling to the magnetic field has this orbital coupling automatically, already in the Hamiltonian level. So the spinon is not far from the electron. So the physics here is not far from a real form liquid.
Sorry, don't you need here spin gapless type of spin liquid for having all this phenomenology? So if you want to have this spinon from a surface, don't you need also to be a gapless spin liquid system?
For this last point, we do not necessarily require the spinon sector to be gapless.
Okay.
So, but in 2 dimensions we have to have that, otherwise it will be confined. In 3D, you can have a gapped matter sector. So, but the essential observation is that we need an external magnetic field to generate internal gauge flux, which is not obvious from the coupling that there is only Zeeman coupling. It's not obvious how that Zeeman coupling comes and modify the internal gauge flux, internal U1 gauge flux. This is the hard part of this one. So in the context of this weak model insert, it's almost clear because at Hamiltonian level we already include the effect of the flux, of the magnetic flux, because of this ring exchange. This if you apply field, not only we have Zeeman coupling, we have this coupling to the external magnetic field in an orbital fashion. So this is basically very much like electrons. But in a strong model insert, there is only Zeeman coupling. It's not really obvious how does this Zeeman coupling come to modify internal gauge flux, right? So,
but magnetic field can couple to this scalar spin chirality, right?
Yeah, this is a very high order thing.
So each time is S1 down S2.
Yeah. Yeah. So
the only thing you need really is some linear coupling between magnetic field and color wave.
Yeah.
So maybe since we are putting here as a strong Mott insulator, we are putting here like, for instance, Robert Schmidt, like in the language of, let's say, there is this classification in terms of Mott insulators and charged transfer insulators. So in this language, so what this paper a long way back by Savatsky, in this language, this Herbert Schmidt is in fact a charged transfer insulator because you have that the upper and the lower Hubbard band are very far away, and what you have in between is in fact the P bands of the ligands.
Mm-hmm.
So it's more as a transfer insulator, and you have to deal with that when you do also considerations, because this is what you find in fact.
Yeah, this is a good point. Yeah.
Charge transfer type of physics.
Yeah, if you.
Which is not in the case of the organic materials.
Mm-hmm,
organic materials, they are genuine Mott insulators. So you have the lower and the upper Hubbard band, and this is what defines your gap.
Mm-hmm.
So I think this is something that you call it weak and strong, but there is this other classification that would call Mott insulator and then charge transfer insulator.
Yeah, that's a good point. One can further just modify this classification a little bit inclusive. For the charge gap is huge. If charge gap is small, then you can include this charge transfer insulator into that. Just regard of this this perturbation process. What's the denominator? Basically, it's the denominator of this perturbation theory to do this super exchange. Yeah, if the denominator of this thing is small, then it's regarded as weak. If this denominator is large, then it's strong. Yeah. So return to the Young-Beck's point. So yeah, it's true. One can have this bisymmetry, but then, so what would be the mechanism to generate this term? We need to have a microscopic understanding how this magnetic field can generate, this coupling to 3-spin product. Right? So there is a distant observation, maybe like 3,000 miles away. But, it's a very distant observation by Patrick and Lagosa, when they try to understand Herpes-Smithite. So they propose this U1 quantum spin liquid with Dirac cones, the Dirac U1 spin liquids. So because of the DM interaction, because of inversion symmetry. There is no inversion symmetry on the bond. There is DM allowed. So it's an antisymmetric DM interaction. So they are observed if you try to measure spin correlation function. In neutron scattering measurement, it always measure pairwise spin correlation function, SS correlation, right? So they try to measure the scalar spin chirality correlation function, which is SSS. So it's a 6-spin correlator instead of 2-spin correlator, right? So neutron scattering cannot really measure this 6-spin correlator. It's a high order, much high order process, right? So you cannot imagine this can be detectable in a regular neutron scattering measurement. So the observation that actually in a in a regular neutron scattering measurement, if you measure pairwise spin correlation function, there will be a proportionality term to the scalar spin chirality correlation function, based on the observation of including of this DM interaction. So yeah, because of DM, so this thing is non-zero already in the Hamiltonian level. This is non-zero. So there will be proportionality term between the expectation value of the spin operator and the scalar spin chirality. So if you measure SS correlation function, there will be a piece corresponding to this correlation of the scalar spin chirality, right? So then you can, this scalar spin chirality is the fluctuation is basically U1 gauge field correlator. So that tells you one can detect this scalar spin chirality fluctuation or the gauge field fluctuation using neutron scattering measurement, right? Right. So this is the hint, right? Although this observation by Patrick and Lagosa is far away from the thermal Hall effect, but really tells you how to generate thermal Hall effect in U1 quantum spin liquid in 2D. So the observation that if you have DM, like this, so if you apply field, the combination of DM, so this scalar spin chirality is approximately equal to this dot this. If you have Zeeman, this is non-zero. If you have DM, this is non-zero. The whole thing will be non-zero. And this thing, the scalar spin chirality is nothing but a U1 gauge flux defined on this by 1, 2 spin, 3 spins. It will be a scalar. It will be an internal U1 gauge flux spanned by these 3 spins. So then you can generate the internal flux distribution by combining Zeeman coupling and DM interaction. So this is the origin of this thermal Hall effect. So as the spin-on moving on the lattice, you will experience this induced U1 gauge flux, induced by the combination of DM and the Zeeman coupling. So then the spin-on bands will be modified, and it will generate a thermal Hall effect.
A question, but even if there was no spin-on, this is still true, right? Even if this from symmetry, if there was spin-on, this would happen today. But if there was no spin-on, even then from symmetry, you will get.
Yeah. So I was reminding you that I will try to understand the physical property of quantum spin liquid. I'm not trying to uniquely confirm in quantum spin liquid. Yeah. So even if it is ordered state, it will have that too, right? But order, we know it's ordered in very beginning. We know it's ordered from other means, right?
Maybe it's hidden.
Yeah. Yeah, so you will generate a thermal Hall effect. Yeah.
On this slide, is this orientation of these arrows correct on this cargo here? C? Should they all point in the same direction?
Which one?
One is minus flux and the other one is plus.
Yeah.
So they should be oriented the other way.
No, it's not. It depends on how you define your how you define this clockwise or anti-clockwise in your product. So the thing is, this depends on the direction or orientation of the induction, and because of that, the flux generated by this effect is not uniform. It's very different from this Motronich's idea where you apply a magnetic field. The flux generated is uniform. So then you get if you look at the spin-on spectrum, there will be an enhanced, the translation symmetry of the spin-on will be realized projectively. Here it's not. So the cell, the unit cell, if you include the flux, the magnetic unit cell is identical to the crystal cell. So there is no effect of that. Yeah, so this provides a way to control the emergent spinel matter, emergent degree freedom with the external probe. Yeah. So then you can do the calculation, you can find that there is a Tomahawk effect. The sign, as I said, these two materials, they have different signs of Tomahawk effect. The reason is because the DM interaction direction is different. That's what we suggest. They have different orientation of DM, so then the sign is opposite. Which is monotonic is sort of obvious. When the temperature is high, all the band have been populated, so then the Berry will cancel, then Berry culture will cancel, will be vanishing. So it's non-monotonic. Yeah, so this is the Kagami system. And recently there are a lot of work, earlier by Frank Portman and others. So they find in this KITP material, if we KITP Hamiltonian, adding Zeeman coupling, there will be intermediate regime, there will be ion quantum spin liquid when KITP spin liquid is being destroyed. And this can be understood as, KITP spin liquid can be understood as a pure pairing of Abrikosov fermion, if you write the spin in terms of Abrikosov fermion. And this is like a pair breaking transition. When the pair breaking transition happens, the system goes to a normal phase, and this normal phase is a ion quantum spin liquid with spinel forming surface. So this state, if you include the DM interaction, which is allowed on honeycomb lattice second level, if you include the second level DM interaction, then you can apply our proposal to understand Tomahawk effect in this regime. Yeah, so then you get a finite Tomahawk effect at zero temperature limit, at low temperature limit. I'm not trying to understand the experiment in this material, in this leucine trichloride. I'm just trying to advocate so this ion quantum spin has a large Tomahawk effect because of if we include the DM interaction here.
In any direction of the applied magnetic field?
Mostly if you apply field.
So you have to do it in the perpendicular direction.
Yeah. Perpendicular direction. Yeah. So this is for this two-dimensional ion spin liquid, you have this mechanism. So for three-dimensional ion spin liquid is mostly by my postdoc, Xiaotian Zhang. Xiaotian is here. He actually more handsome than yeah, this reminds of Hollywood movie when there is opening, there is a line, right? It's a drawing line. So
this MGM.
Yeah. Yes. So the in this context, actually we do not require DM interaction. The Zeeman coupling coupled to so-called Z component of the spin. This is because of this particular realization of this elastic gauge theory. So the Z component of spin in this particle ion spin liquid is nothing but so-called emergent electric field. This is nothing but the emergent electric field. So in 3 + 1 dimension, this thing is described by compact ion elastic gauge theory, compact quantum electrodynamics. So there are emergent magnetic monopoles. Some people call it dual monopoles. So the magnetic monopoles see this induced E field as a flux. Just the electrons see magnetic field as a flux. So the monopoles see this induced E field as a flux. So then we apply external field that induce the internal. This will be non-zero, and this is the induced E field. So then the magnetic monopole will see this E field as a flux. So then we generate a non-trivial Tomahawk effect due to the induced E field. So there will be a monopole Tomahawk effect, magnetic monopole Tomahawk effect. So some experiment has done a long time ago by Ong. It's a paper on Science, 2012, I think. Yeah. So there's some other works, but using Schrödinger bosons, and also consider scalar spin chirality, but did not interpret in a gauge field fashion, because it's a Z2 spin liquid here. Let me summarize the second part. So we point out that there is a physical origin of the emergent Lorentz force on the spin-ons, and obtain the resulting we call it a topological thermal Hall effect because this spin chirality scattering thing is used to understand the topological Hall effect in this itinerant magnets, where you have background skyrmion when electron moves can experience the background flux generated by the skyrmion, and this effect is called a topological Hall effect. And the physics here is quite similar, but it's a thermal Hall effect. So we call it a topological thermal Hall effect, just using the similarity of the mechanism. So we established the connection between the microscopic interaction and the emergent fractional degrees of freedom and provide a scheme to control these degrees of freedom. So this result can be extended to other non-central symmetrical quantum spin liquid. This actually does not require to be non-central symmetrical. As long as you have DM, you would most likely have this effect. Yeah, so in the end, the thermal Hall effect, thermal transport in molten inside are not really well understood. Yeah, there are still a lot of opportunities. Yeah, thanks.
Nice talk. Questions, comments? Yes.
In these scenarios where you have DM interaction, can you comment on the orientation dependence of the thermal Hall effect, let's say for the orientation of magnetic field?
Yeah, so I can give a small comment. So if you have a different different orientation of the field has two effects. First, if this DM is this direction, then the projection of this field direction along this direction will generate flux. But field itself will also split the spin-on band. You have two effects. It's that these two effects together give you this angular dependence. Yeah.
But the plot you have for this edge, this is an edge which is taken perpendicular. So it's the 1-1-1 direction.
Yeah, this is a 1-1 direction.
Yeah. So if you take any other field, because we know that this phase, when you put d equal to 0, this phase is there when you have this 1-1-1 direction. So how many different fields did you look at? Directions.
In the presence of DM, you mean?
In the presence of DM, yeah.
Just the 1-1-1 direction.
Just this one.
But I mean, I would say presumably stable for
quite a long.
Probably, yeah.
Because you only have the KITP. Federico.
Concerning the first part.
Yeah.
Can you remind me the phase diagram of this easing model in transverse field at zero temperature? What
it will always be three subjects. As long as you turn an infinitesimal magnetic field, transverse field, it will generate this three subjects order. Yeah.
So as a function of h, you have a phase transition.
No, so as a function of h, there will be phase transition. When field is very large, you get all the spin will be in the transverse direction, which is what we call a disordered phase, right?
The other side is
the other is this three subjects order,
which is gapless according to you.
Well, the system doesn't have any symmetry at all, so there is no reason why it should be gapless.
No, but if you measure the dynamical structure factor, this is gapless eventually, correct?
No, eventually it should be gapped, but it can be a mini gap that cannot be visible in experiment. So the system doesn't have any symmetry at all. Why it should be gapless? It's a discrete symmetry. All the eyes symmetry.
I was surprised that according to your picture,
yeah.
It seemed gapless. Instead, it's gapped.
No, so it cannot be gapless. You're always gapped.
I mean, in that case, is the fact that it's apparently gapless related to the fact that the J1 and the H term are of similar magnitude?
No, it should be gap. I don't understand the question.
I mean, let's say the gap appears to be small in the inelastic neutron scattering.
Yeah.
From the plots, is that related to the relative magnitudes of the interaction terms and the effective ones?
No, I think it's because the system is highly frustrated. There is a lot of degeneracy if you turn off the transverse field. So even if you add the transverse field, there's still some remnants of this frustration. You can see some very small gapless excitation going on. Yeah, the system doesn't have any continuous symmetry. There's no reason.
Yeah, but from the figure, it's a bit confusing.
Why it's confused?
I was confused.
Can we discuss this later? But this a little bit of detail. Yeah.
There are any more questions or comments?
Question maybe?
Yes.
This may be a hard question. Okay. From your thermal Hall, if it were not a so the one can imagine two situations where it is the actual spin-on, in the other case it's not. Is there some way to estimate the confinement length scale from some, so that at least you can then you have some hope of getting whether it was actually because of spin-ons or it was just something because of confined. Is there some length scale to extract from some
No, this is a difficult question. I don't know.
So we can go back now to Federico's question.
Yeah, I think there can be some. Yeah, this can be some order. It's order by disorder effect. That can generate this. Eventually, it should be gapped. It should be gapped. It's just it's not discernible. Lucille has this kind of order by disorder. It can have the pseudo gap, pseudo ghost mode. The system doesn't have continuous symmetry, but if you take care of these degenerate, degenerate classical ground states, that looks there is a continuous symmetry, and then you break it by quantum fluctuations. It looks like the excitation has some gapless mode, but really it's the gapped. There is a mini gap. It's not discernible experimentally. They call it a pseudo ghost mode.
Even theoretically.
Yeah, theoretically, yeah, should be gapped. Yeah.
But sometimes, if you do linear spin-wave theory, you can have a gapless mode. If by the time you add any anisotropy, it just gaps.
Yeah.
So I have a question on thermal Hall. So when these experiments came out, there is a nice work by Lucille, Leon, and also Achim Roche and his postdoc where they showed that you need to include the phonons in your description. So are you also taking this into consideration when you're talking about thermal Hall in general, especially for this type of experiments or materials?
Yeah, so
you have this coupling to the phonon, degrees of freedom. So are you also taking that into account?
No, I'm not taking that into account. In the context of Lucille and Leon and Mengxin and Achim Roche and others. So over there, the reason they consider phonon is because of this particular experimental setup by Yuji Masuda. So I'm just considering more generally, how do this quantum Hall effect can appear in a quantum spin liquid. Yeah.
Questions? Otherwise, it's time for lunch. Thank you very much.
Yeah, thank you.